All right. Hello, everyone. In this video, I am going to present you the work entitled Causality-Based Explanations in Multi-Stakeholder Recommender Systems. The team that worked on that project is composed of Marcel, Nicolas Labroche, Clément Moreau, and I, Willeme Verdeaux. We are all from the University of Tours in France. So without further ado, let's dive into it. So the two main contributions in our work is firstly a new formulation for the multi-stakeholder recommender system problem, where we represent each stakeholder with a profile. And so we are able to evaluate a given ranking for all stakeholders in the process. Then we are just making the sum of all those evaluations for each stakeholder, and we basically try to maximize this sum. The way we are getting those evaluations is by using the well-known and very popular metric, that is the normalized discounted cumulative gain. Though it is interesting to note that the formulation is metric agnostic and other gain-based metric can be used. We will go in more detail later with the formula. Secondly, we are proposing a new definition of causes and a way to extract explanations based on that causes. We are mainly trying to follow the Pearl causality framework, and more specifically, we borrowed Melius formalism, which is also based on Pearl framework. Also, I will go more in detail further in the video. You might wonder why the multi-stakeholder recommender system problem is a complex one. It is mainly because the objective is to find a solution that maximizes possibly conflicting utilities for multiple stakeholders at once. For instance, Burke, in his work published in 2016, represents an utility space where each solution is a tuple yielded by a recommendation algorithm. Each component of this tuple is the utility score of a particular stakeholder yielded by the chosen algorithm. Then they will choose an algorithm that produced a solution on the Pareto front of that utility space. Generally, in the literature, this problem is solved as a post-processing, and what we mean by that is that, first of all, a user-centered recommender system is first applied before taking into account the other stakeholders. Also, genetic algorithms are often used because the search space is very large, and in our case, we used a simulated annealing. You also might wonder why the explanation of recommender system is a crucial problem. It is because having an explanation that backs up a recommendation helps building trust in the algorithm, and also the perceived quality of the system increases. Without that, the user might not trust the recommender system and not even use it. The explanation can have various forms. Some of them are quite simple, such as non-personalized explanation. Other customers also bought this or that, which are already in use in practice. They are also a collaborative way to extract explanation, which is, for instance, we recommended you this product because you like sports and you are between 18 and 25 years old. And then we have visual explanations such as tag clouds, which are cognitively more difficult to comprehend, but on the other hand, is quite appreciated based on user studies made. We could also borrow some interesting ideas from other domains like the explainable AI. And then there are also the counterfactual analysis, who could be seen as well as explanation. It is analysis that answers questions such as what would have happened if that or this. This schema represents an overview of the way we are extracting explanations. At the beginning, we have a set of events, which could be seen as our start universe. Then we are going to intervene on this universe by removing events. There are as much as universes as there are ways to remove events. That's why there is layer here. We are going to remove gamma, which is the contingency set, and the event he, which is the event we want to determine if it's a cause or not. And so if by doing that, the profile sigma is different from the one we had at the start, it means that the event is a cause in that universe. Furthermore, all causes are gathered here, and some patterns are extracted and are formatted as human readable information and pushed to the user or stakeholder. So more formally, let's assume a set of object O, which could be, for instance, a catalog of product from an online shop. Those objects are described by properties useful for the pattern extraction. A set of stakeholder S and R, a set of roles such as system, user, or provider. A set of events E, composed of vectors with 4 attributes. The stakeholder who is doing the event, S, the object O, that could be purchased, for instance, R, a real value which describes the interestingness that S has for O. It could be a rating or a quantity purchase or anything else. And finally, a timestamp. Each stakeholder has some preferences derived from the event. In our case, it is consumptions. So we can sort the object consumed by their interestingness, measure R, but not the one he or she did not consume, obviously. Then those preferences are transformed in profile or sigma S, where for each object not consumed, we are going to predict the R with a recommender system. So here is our multi-stakeholder recommender system formulation. So at the time we have to make a recommendation, the objective is to find a permutation or a ranking sigma star that maximizes this weighted sum. We want a sigma star that is a good compromise for every stakeholder we are taking into consideration in the recommendation process. As I said, Q is interchangeable, and it is interesting to note that we can bias the recommendation thanks to alpha. So we are making a distinction between explaining sigma S and sigma star. Here in this slide, we are going to discuss the explanation of sigma S, or the profile. So for a stakeholder S and a set of events E, we can derive or obtain a sigma S. That's what this symbol here means. Then we say that given an event E, the small e, if by just removing that event from our starting universe and we obtain a new profile, which is different from the starting one, then this event is called a counterfactual cause. Also, if the event is not a counterfactual cause, it could be an actual cause. And so we have to remove from E, the big E, a set of events called gamma, the contingency set, before E become impactful when it's removed. And so the bigger is gamma, the less impactful is the event. In order to measure this impactfulness, we have a metric called the responsibility, which is based on the gamma set. Note that if the event is a counterfactual cause, the responsibility is maximal. The way we are explaining sigma star is a bit different from the way we are explaining profiles. I want you to recall that we want personalized explanations. So for a given stakeholder, we want to explain to him why sigma star is the way it is. Our intuition was to find events from other stakeholders that made sigma star deviate from the profile of S. Let me explain with a small example. Let's assume 3 friends that are the stakeholders and they want to be recommended some movies to watch. So the recommendation has to take into account their profiles. 2 of them did watch a lot of horror movies and the other one not so much. He or she is more into sci-fi films. Obviously, the system will generate a sigma star with mainly horror movies on top, and we want to explain that to S, who does prefer sci-fi films. So by removing the events concerning the horror movies, we should change sigma star but not sigma S, because now sci-fi events might have more weight in the output. And we should also increase the perceived quality of sigma star for S. That's what we say with those rules here. So we need the set of causes in order to generate the explanation. And this is true for both sigma S and sigma star. Moreover, we compute the responsibility of each cause, and with this responsibility, we can further discard some of them based on some threshold if we think that they are not relevant enough. We then mine pattern on all the objects from those events that we identify as a cause. And specifically, we return the most frequent value for each properties of object. Now that I have presented the theoretical framework, it is time to put things into practice. Our experimentations have been done on the Calidea Up Company dataset. Its main activity is to sell management software to work consile. We can see a work consile more or less like a special shop for workers in a company. The dataset is composed of purchase transaction from 2014 to 2018. There are a total of 5,840 workers who did consume 540 different items or services, and it represents 168,000 transactions. Each transaction is equivalent to an event defined previously. So, first of all, we have made experimentation about our formulation for the multi-stakeholder recommender system problem. We defined two types of stakeholders or two roles. The first one is the end user or the worker, and the second one is the work consile or the system. User profiles are computed thanks to the surprise API and more specifically with the nearest neighbor recommender system. The work consile profile is based on the subsidies, or in other words, it is based on the discount granted to the employees when they purchase things, with the idea that the more a consile is discounting an item, the more it wants it to be sold. We then define different scenarios. The first three are for testing the impact of alpha on the sigma star. The remaining ones are for testing the impact of the number of stakeholders within the recommendation process. As I said previously, in order to compute sigma star, we used a simulated annealing, having as objective function the formula presented previously. It searches for a solution that maximizes that formula. And what we can say is that it gives satisfactory results. It also shows that we can favor a stakeholder using the parameter alpha without damaging too much the global NDCG. We also noticed during our experiments that the number of stakeholders seems to have almost no influence on the score of NDCG for sigma star, though we think more tests should be done before really taking any real conclusion on that point. Secondly, we have made experiments for our explanation framework. It is really a complex problem because we might have to explore possibly the power set of E. That's why we have restricted our experiments on very small subset of E ranging from 8 to 14 events. That is a bit far from your use case where the set E can be very large, but it's a starting point. We use the following protocol. We randomly selected events from the Calidea Up dataset and search for causes using our framework only for sigma S by now. We used a different predictor this time. We used the baseline predictor because the training phase is quicker than nearest neighbor, where every time we remove an event, we have to recompute the similarity matrix. Here are the results in execution time when we gradually increase the size of E. We clearly see that the growth is exponential as expected with the power set to explore. We can also notice that the training phase is not as sharp as we thought, but it is still quite consuming. So it is a very expensive process. We made that last experiment to assess how the responsibility metric behave. So to compute the responsibility, I recall that we need to find the smallest contingency set that makes the event become a cause. So if the event is a counterfactual cause, it means that gamma is empty and the size is 0. Interestingly, it seems that the distribution is binary in the sense that either an event is a counterfactual cause or not a cause at all. So to conclude this presentation, I would like to say that our solution is not quite close to be set up in a real case environment. We need to come up with a more tractable resolution. We have already envisioned several ideas, such as hill climbing or beam search during the lattice exploration. We could also focus our attention on specific recommendation algorithm and more practical problem. We would also like to evaluate other approaches for the sigma star resolution because we are not really satisfied about the simulated annealing, and we would like to implement a non-post-processing method. Finally, I think the culmination of this work would be when we will have a user study confirming that our work is useful and relevant. I am looking forward to hear your questions. Thanks for watching. Bye-bye.